So now we've covered the magnetic field due to a moving charge reasonably well. What about finding the magnetic field due to a current carrying wire? So in our picture, we see a little charge q. It's moving with a velocity v. We might imagine that it moves to a new distance, which is delta s away, and it would take an amount of time, delta t, to get there. So that a bit of charge, since it's moving, it'll cover some distance delta s and it'll take some time delta t. Okay, so that's one thing we know about a moving charge. Another thing that we know about current is that current is flowing charge. That means that our current I is our charge over time. So now we'd like to put these things together in our Biot-Savart law. I've got the Biot-Savart law written out here. The part we'll focus in on is the QV cross R hat. And let's see what that gives us. So QV cross R hat, that's going to equal to Q. Now V is the velocity. V can be approximated as delta S over delta T, and that's going to be crossed with R hat. Now, V is an approximation of delta S over delta T, but if we'd like for our approximation to become more accurate, then we should take our delta S to be very small. So delta S is small. If delta S is small, that means that instead of writing delta S, we write ds. So we only take a little small part of the path. If we're only using a little small part of the path, we don't get the total magnetic field created. We get a little bit of magnetic field created. So when our charge moves over a small bit of path, it makes a small bit of magnetic field, dB. So that's how we're going to deal with delta S. So that goes to ds. And then in our equation, we might notice that we have Q over delta T. That's current I. Okay, let's put those things together. So our magnetic field created is a small amount of magnetic field. That's equal to mu naught over 4 pi. QV cross R hat is the same as I ds cross R hat. And then everything has to be divided by R squared. So since our path, our charge is only moving a small distance, it means we don't have to restrict ourselves to straight line motion. So we can have any sort of a wire in any sort of a curvy shape. And the charge moves over a little bit of a path over a small distance. And that small distance is called ds. ds is the small bit of the path or a small bit of wire. So now this leads us to a final result, which is an alternate expression for the Biot-Savart law. If we'd like to get the total magnetic field B, we have to add up the magnetic field due to each little bit. So we would do the integral of dB, which is the integral of mu naught over 4 pi times I times ds cross R hat over R squared. R is still the same thing. It's your vector from the point you're talking about to the place where you'd like to find the magnetic field. So now we have two forms for our Biot-Savart law. One depends on the charge and the velocity. The other depends on the current. Let's use our alternate expression of the Biot-Savart law now to find the expression for the magnetic field around a long straight wire. The Biot-Savart law applies to any shape wire. Let's do a long straight wire because it's the most straightforward example. So I've got drawn in my picture here a long straight wire. I put in a coordinate system. I put the x-axis going down through the center of the wire, and the y-axis bisects that wire. I'm going to try and find the magnetic field at some point P, which we'll say is a distance y above that wire. So this is what we're looking to find. Why don't we take this a little bit slowly and let's fill things in step by step as we go. So let's start with writing down our expression for the Biot-Savart law. Our total magnetic field is what we get by summing up the contribution due to each little bit of field. So we add up all the small pieces of field to get the total field. Each small piece of field is given by the Biot-Savart law, mu naught over 4 pi times the current I times ds cross r hat divided by r squared. Looks like the next thing we should do in our expression is let's identify what do we mean by ds, what do we mean by r, and what do we mean by r hat. So ds is a little bit of the path along that wire. So we just pick some small segment. So there's our ds. R is our vector from ds to our point P. So there's our vector R. And r hat is our unit vector that points in the direction of R. Hopefully that's pretty clear. Let's put in that our distance from our little element of wire to the origin is a distance x. Okay, next step in our integral, let's take our constants out front. Mu naught is a constant, current I is a constant, and 4 pi is constant. So now we're outside the integral of ds cross r hat over r squared. If we'd like to find the magnitude of our wire, because we'd like to find the magnitude of the magnetic field, because we can find the direction from our right-hand rule, we know that the magnitude of the magnetic field is equal to mu naught times I over 4 pi times the integral of the magnitude of ds cross r hat divided by r squared. Okay, the next thing we have to tackle is what is ds cross r hat. So let's start to sort out now what do we mean by the magnitude of ds cross r hat. So for the magnitude of ds cross r hat, we remember that the magnitude of the cross product is the magnitude of ds times the magnitude of r hat times the sine of the angle between them. So we could just write that as ds. Remember that the magnitude of a unit vector is just 1. That leaves us with ds times sine theta. So now we have to sort out what do we mean by ds and what do we mean by sine theta. ds is our length element. It's a little bit in the horizontal direction. So ds is equal to dx because it's a small bit in the horizontal. Okay, what about theta? Well, theta is our angle between our unit vector r hat and our length element ds. We might notice on our diagram that it's a right angled triangle, which means that r is going to be the square root of x squared plus y squared. Sine theta, which is opposite over adjacent, is equal to y divided by r. Okay, so our sine theta is y over r. Let's put that in our equation. Okay, and now let's pop in our magnitude of ds cross r hat in our expression for our magnitude of our magnetic field. So the magnitude of B is mu naught times I over 4 pi times the integral of dx times y. That's over r times r squared. Okay, so that's mu naught times I over 4 pi times the integral of y over r cubed dx. We can take our y outside if we wish, and we can remember that r is the square root of x squared plus y squared, or x squared plus y squared to the 1/2. And we're going to be cubing that r, so we'll get an exponent of 3/2. So our final result then is that b, the magnitude, is mu naught times I times y. Our y is a constant value. That's why it can come out front of the integral. So out of the integral of dx over r cubed, so x squared plus y squared to the 1/2, that's cubed, so we get an exponent of 3 over 2. Okay, so that's how we're going to find our magnetic field, the magnitude of our magnetic field around the wire. To find the magnitude of our magnetic field now, we'll have to carry out the integral, which means we need to know the limits of the integral. We have a long line of current. A long line means infinite. So if we wanted to put the limits of our integral on, it would technically go from minus infinity to plus infinity. Now, infinity is funny. If we do our integral from minus infinity to plus infinity, it doesn't really account for the direction of the magnetic field or the direction of the infinity. And if you try that, you'd actually end up getting a total magnetic field of 0, which we know is not true. So let's try another tactic. Let's say that we know that the magnetic field for the entire wire would be equal to twice the magnetic field of half the wire. If we wanted to find the magnetic field of half the wire, that would have a limits of an integration from 0 to infinity. That's not so funny when we try to solve it. So we're going to do 2 times our integral times our expression for the magnitude of our magnetic field. So 2 times mu naught times I times y divided by 4 pi times the integral from 0 to infinity dx over x squared plus y squared to the 3 over 2. This integral is not too tough. You can either work this out yourself, or you can look up your result in a book. It's fine whichever way you choose. So we've got 2 times mu naught times I times y over 4 pi outside of. The result is x over y squared times the square root of x squared plus y squared. And that's evaluated at 0 and infinity. So let's look at the two limits. What do we get if we take x approaches infinity? So as x goes to infinity, our expression of x, hang on, so I've got a y up top here and a y squared down here, so they cancel. So we've got x over y times the square root of x squared plus y squared. You can't really put infinity on top and infinity on bottom, so let's multiply the top by 1 over x and the bottom by 1 over x to see what we get. So that's a 1 on top, and on bottom we've got y. 1 over x is the same as the square root of x squared, so I can multiply that inside my square root sign. So that's x squared over x squared plus y squared over x squared. X squared over x squared, that's equal to 1, whether x is infinity or not. Y squared over x squared, if x gets really big, that whole term goes to 0. And then our result for our limit is it's just equal to 1 over y. Okay, that one wasn't too tough. What about if x equals 0? Well, that one's pretty easy too. X over the square root of y times x over y times the square root of x squared plus y squared, if x is equal to 0, is just equal to 0. So now, well, this, I think I can squeeze in my result up here. That gives us, for our magnetic field then, it's equal to 2 times mu naught times I over 4 pi. Then we'll put in what we got for our results, 1 over y minus 0. So we're left with 1 over y. So there's the magnitude of our total magnetic field of that entire wire. Let's simplify that equation a little bit and make sure we understand what it's telling us. So the magnitude of the magnetic field of the wire at some distance y away from it is equal to mu naught times I over 2 pi. So in that expression, I just took my 2 into my 4. I got left over with a 2 on the bottom, times 1 over y, so I've got my 1 in the denominator. This is telling me that the magnetic field only depends on the distance from it. It's uniform with the distance from it. That tells us that the magnetic field makes circles. Okay, what's the direction of those circles? Well, if you apply your right-hand rule, if you remember your Biot-Savart law, so we said that B is equal to the integral of mu naught over 4 pi times I ds cross r hat over r squared. To get the direction of the magnetic field at point P, you point your thumb in the direction of ds, point your index finger in the direction of r hat, and then your result shows you the direction of your magnetic field. That's going to be out of the page. That's your middle finger. So B is out of the page. So you can take that, and this is just like when we did the moving charge, finding the magnetic field at different points. You can use this result to show the orientation of those magnetic fields. So the orientation is with the right-hand rule. So what if we took our wire and instead of looking at it in the 3D picture, what if we look at it like this? So I'm going to draw a new picture. So here's our eye looking down at the wire. The current is coming towards us because the current goes in the same direction as our ds. So the current is coming at us. That's a dot in a circle. Our magnetic field is making big circles with a radius equal to y. And then the orientation, if we're looking at it, comes around this way. This matches the right-hand rule that we described when we started this section. So the right-hand rule is the same no matter which way we're looking at it. It always gives the same answer. So I'm just going to go on to the next slide and we're going to write down the general result because we don't generally represent the radius with a y, we generally use an r. So typically when we work on these problems, we say we're trying to find the magnetic field at some distance r from the wire. That magnetic field is going to make big circles around the wire, and the orientation is going to be given by the right-hand rule. So I've sketched it in 3D. It's pretty hard to draw in 3D all the time, so if you want to take an edge view, that's often pretty good. So you draw your current on your wire. In this case, the current comes towards our eyeball. And then remember the right-hand rule says you stick your thumb with your current and you make a circle with your fingers to show the orientation of the magnetic fields. And then instead of writing our magnetic field with a Y, we write it with an R. So we say B is equal to mu naught times I over 2 pi R with a direction given by the right-hand rule. So there's the magnetic field around a long straight wire. Let's start with a pretty straightforward example. What is the magnetic field at a point P, which is 10 centimeters, from a wire carrying current 0.75 amps? So you can look at the side view or you can look at the top view. Let's use our equation to get the magnitude first. B is mu naught I over 2 pi r. So r is your distance between your wire and your point. Your current is 0.750 amps. Your distance is 0.10 meters. That gives you a strength of magnetic field equal to 1.50 times 10 to the minus 6 teslas. To get our direction, we'll use the right-hand rule. Let's use the right-hand rule to find the direction of the magnetic field in a current-carrying wire at point P. So the current in our wire goes straight up and we'd like to find the magnetic field right here. So let's say my pencil is my current. I know my magnetic field makes big circles and I'm trying to find the magnetic field at this point right here. So to use my right-hand rule, I put my thumb with my current and my fingers show the orientation of the field. So I ask, what's happening right here at this point? Well, my fingers are pointing down into the page. My magnetic field is a tangent to the circle, and my fingers are pointing down or into the page. I can draw that on my picture right here. So my magnetic field is into the page. If you were just going on the picture yourself, you would put your thumb up with the current and you would ask, what do your fingers do at point P? If you want to go for the 2D view, so this is the top view, for 2D, let's say that we're going to put our eye up here and we're going to look downwards at our wire. So all this means is we're going to twist it. So now the current is coming towards us. So our current looks like this. Our magnetic field makes big circles around that wire. We can draw those circles. We're trying to find the magnetic field, a distance r from our wire. So let's ask, what's the orientation of those circles? Our thumb goes with the current and our fingers are coming around the circle. So at point P, what are our fingers doing? Our fingers are going straight up. So the magnetic field at this point points this way. So you can go for the 3D view or the 2D view. It doesn't matter, but either way you'll use your right-hand rule to find the direction. Now we've got our magnitude and our direction. We put it all together to say that our magnetic field is 1.5 times 10 to the minus 6 teslas, which points into the page. If you want to put in an XY coordinate system, you can do that in the system I've drawn. Into the page is the same as minus k hat.